Hello, today we will learn about DES algorithm and its working. We also see what are the steps of generating a round key, what are the encryption and decryption process, what are weak keys, and at last we will see some example. So let's jump straight into it. So DES stands for Data Encryption Standard. It is a block cipher algorithm that takes a plain text in a block of 64 bits and converts them into ciphertext using a 10 keys of 48 bits. It is a symmetric key algorithm, which means that the same key will be used for encrypting and decrypting the data. Since DES is based on Feistel Cipher, all that is required to specify DES is round function, that is 16 rounds for in this case. Second is key scheduling, that is generating a round key, and third is additional processing like initial and final permutation. So the first step is generating a round key. We take a 64-bit input and we pass it to the parity drop. It drops 8 bits and pass on to the rest of the 56-bit using PC1 table. You can see PC1 table in the right part. Then we divide 56-bit into 2 halves and it is left shifted circularly. For round 1, 2, 9 and 16 it is shifted by 1 bit, and for other round it is shifted by 2 bits. So after shifting is done, let's pass these two halves into a compression P box. It is a compression P box and it gives an output of 48 bits. This procedure will happen 16 times and will generate 16 round keys. This compression box is done by PC2 table as shown in the right part. Now let's start encrypting the plain text. So here is a general diagram of DES algorithm. Here we take a 64-bit plain text as an input, a key, and it generates a 64-bit ciphertext. We already generated a round key. Then let's start the procedure. So first step is initial permutation. It is just a straight P box and it just reassembles the bit. Then the result will be passed to the round one. Okay, after initial permutation, we divide 64-bit into 2 halves, 32-bit each. The right part goes into expansion permutation, that is expansion P box, and generate a 48-bit output. This result will be XORed by a round key and then pass it to the compression S box. The compression S box is shown right here. So it takes a 6-bit and convert them into 4 bits. So the 48 bits will be converted into 32 bits. After this happens, we will pass it to straight P box, that is for permutation, and it is also just reassembles the bit, and after that the result will be XORed by the left part and the output will be stored in the right part. For the left part, initial value of R will be directly copied to the left part and we will merge them, and after merging it will become 64-bit, and this procedure will happen 16 times. And after that we apply a final permutation. It is also just a straight P box and it's only reassembles a bit and gives a 64-bit ciphertext as an output. So this was the encryption process. Now decryption process. In the decryption process, all things are same, just we will reverse the round keys. Like the key 1 will become key 16 and key 2 will become key 15 and key 16 will become key 1, and all other process is same. Now let's see what are the weak keys. A weak key is the one which after parity drop operation consists either all zeros or all ones or half zeros and half ones. So what the key scheduling does is it sends only permutation and shift operation. So if we shift or permute all zeros or all ones, it won't change a thing. So all 16 sub keys will always be the same. So this kind of keys are known as weak keys. So if we encrypt twice using these keys, we will get the same answer, because reversing the key won't change a thing because all 16 are same. So that's why we shouldn't use these kind of keys. There are 4 weak keys in DES algorithm. One is 0 and alternate zeros and ones. Second is alternate F and E. Third is E and 0 alternate up to 8 bits, and F and 1 alternate up to 8 bits. And last is 1 and F alternate for 8 bits and 0 and E alternate for 8 bits, like you can see here. So let's see weak key explanation. So as I said before, in decryption, the 1648 bits key are just reverse. The 16th key become the first key, and the 15th key become the second key, and so on. So when all the keys are same, there is no meaning of reversing a key, or like if all 16 keys are identical, then if I reverse them, it won't change anything. So it is same as before. So encrypting 2 times will be treated as encrypting 1 time and decrypting 2nd time. So when we encrypt 2 times using a weak key, it will again generate the plain text. So we should avoid using weak keys during encryption. Let's see using an example why shouldn't we use a weak key. Given key is alternate zeros and ones. Our plain text is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So we have to encrypt this plain text twice to see what are the result. So we have given a PC1 table here, and we also have given a PC2 table. So this is the expanded binary form of the key. Let's take a look in this table. So our key is this. Its expanded binary form is this. So let's apply PC1. You should remember that PC1 only reassembles the bit and drop 8 bits from the key. What PC1 table says that the 57th bit of the binary format will become the first bit, and for 49th bit will become the second bit, and so on. So let's see what the 57th bit is. 57th bit is 0. So the first bit will be 0. The 49th bit will be 0, and the second bit will be 0, and then 41, 33, 25. The 41th bit here is 0, so the third bit will be 0. 33th bit is 0, so the fourth bit will be 0, and so on. We will perform for this 56 times and get the result. As you can see, the 1 consists at only multiple of 8 places, like at 8 the 1 appears, at 16 the 1 appears, at 24 the 1 appears, at 32 the 1 appears, and as you can see in PC1 table, there is no multiple of 8. So all these 1s are dropped and all these zeros are the remaining one. So after that, after PC1, we will apply the left shift. For left shift, we are generating the first key. So let's shift all these bits by 1 bit, because first, second, 9th and 16 are left shifted by 1 bit and all others are left shifted by 2 bits. So we will left shift these by 1 bit. So we get the same answer because all bits are 0. So no matter how many times we left shift this, we will get the same answer. Now apply PC2. PC2 table looks like this, and it says 14th bit will become the first bit. So is the 14th bit. This bit will become the first bit. and the 17th bit will become the second bit. So here is the 17th bit and here is the second bit. Because all bits are 0, no matter how we substitute them, the result will always be a list of zeros. Then we convert this binary format to hexadecimal format. We get a final result for key 1. And similarly, we do the next step. So we get a first round key, all zeros. Similarly, for the remaining rounds, we will get all zeros up to 16. I have shown till 10th, but it is up to 16th. Now, let's start encryption of the plaintext. There are total 10 steps in encryption. First is apply initial permutation. Second is divide it into two parts. The third step is take a right part as an input of an expansion p box. Then XOR the result with the key. Then the result from step 4 will be passed to compression S box. Then it will pass to the straight P box, and at last, step 7 XOR with L0 and store it into R0. After that, step 8 is pass initial R0 value to the L0 and perform this step 2 to step 8 16 times. Then step 9 is to swap again R0 and L0. And step 10 is to apply inverse permutation, that is final permutation, so that we can get a ciphertext. So let's perform each task one by one and see what is the result. Our first step is initial permutation. Our plain text is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, A, B, C, D, E, F, as you know. So convert this into binary form. So here is the binary form of this hexadecimal value, plain text. Now pass this binary format to IP1. Sorry, this is not PC1, this is IP1. So as you can see here in IP1 table, the first bit will be 58 bit, the second bit will be 50th bit, and the third bit will be 42 bit, and the fourth bit will be 34th bit, and the fifth bit will be 26 bit. So let's rearrange them and see what we will get as a result. So the first bit will be replaced by 58th bit. So our 58th bit is 1. So the first bit will become 1. The second bit will be from 50th bit. So the 50th bit is also 1. So our second bit will also be 1. We have a 0 on 42nd position, and hence we get a 0. Now let's check a random bit like this is 9th bit, and the 60th value will be at 9th bit. So what we got at 60th position, there is 0 at 60th position, so at the 9th bit we'll get a 0. So therefore we will fold all this value by seeing IP1 table, and we get a result CC00, CCFFF0AA, F0AA. So there is the output after applying initial permutation. So let's divide this 64 bit into two halves. Left part is this and right part is this. And our first round key is 48 bit round key, all consisting all zeros. Now we apply all steps of round 1. Here's the key of 48 bits, and here's our left and right plain text of 32 bit each. So we pass R0 to expansion P box. Here's an expansion P box, and it is nothing but joining the left adjacent bit and joining the right adjacent bit. As you can see, 0, 1, 2, 3, 4. Its left adjacent bit is 32 and its right adjacent bit is 5. And then 5, 6, 7, 8, 9. Its left adjacent of 5 is 4 and right adjacent of 8 is 9. Now, the right bit, the 30th bit is 0. So, we add a 0, then 4 bits are copied as it is, and the 5th bit is copied next to it. So, the next 4 bit, for the next 4 bit, 4th bit is 1, the 4th bit are copied as it is, and the right adjacent bit is 1, and it is there. Similarly, we apply the expansion p box to the rest of the bits and generate a 48-bit text. Now the next step is to XOR the result with the key. So as we know, if we XOR any value with 0, it returns the same output. So as we know, the key consists of all zeros. The output will be same as the result. So this column will as it is get copied to the next column. Now the result will be passed to the compression S box. The compression S box table looks like this. So we pass the 6 bit to this table and we get a 4-bit output. So how do we do this? We take a first and the last bit and convert it into the decimal format, and the rest of the bit we will convert also into decimal format, and we will look at particular row and column and find the value. So combining 0 and first and last bit, it gives us 0, and combining the rest of the 4 bit, it gives us 15. So we will check 0 and 15, so we will get us 7 output. So we convert 7 to the binary format and we get an output of 0, 1, 1, 1. Similarly, we apply this method to the remaining bits and we get an output. Now, the S box will give us 32-bit output. Now, we will pass this result into state P box. The state P box is shown here. So the first bit will be 16th bit, the 7th bit will become the 2nd bit, the 20th bit will become the 3rd bit. So let's check it. So 16th bit is 0. So the first bit will become 0. Then 7th bit is also 0. The 2nd bit will become 0. And then the 3rd number was 20 and 21. So the 3rd number is 1 and the 21th number is 0. So the 3rd number will become 1 and the 4th number will become 0, and so on we will do for remaining bits. So we will get all values of state P box. Now at last we will XOR this result with L0 and store it into R0. So L0 is this and state P box values are this. When we XOR 1 and 0, we will get 1. Similarly, for second, 1 and 0 will get an output 1. For third, 0 and 1 we will get an output 1. For 0 and 0, we will get an output 0. For 1 and 0, we will get an output 1. For 1 and 1, we will get an output 0. And similarly, we will perform this step 32 times and get the result. So when we get the result, we will convert this binary value into hexadecimal value and store it into R. And for L, the initial R value will be stored into L. So after first round, we'll get right equal to EB5, B0E, C5, and the left equal to S0AA, S0AA. Similarly, for 15, we will perform all these steps 16 times and we will get this result. And after 16th bit, we'll get this and this as a result. Then we will perform final permutation and we'll get the ciphertext this. Final permutation is same as initial permutation, just some values are changed. The final permutation is just the inverse of initial permutation. So as a result, we get ciphertext this. Okay. Now we will pass this ciphertext to for the second encryption using the same key. So this ciphertext is passed for second encryption, and after initial permutation we get this. Initial permutation, as we have seen before, is the same. Then there are these are the value after each round we will get. So after the first round we'll get this value, and as you can see, these values are nothing but the values of after round 15, just in opposite manner, right? The right value is the left value, and the left value was in the right value. And similarly, you can see all these values are just reverse of each other, and we get the ciphertext same as the plain text. So we conclude that using a weak key, it reduces cipher complexity. So we should avoid using weak keys while encryption in DES algorithm. You can also find Google Colab link in the description, so you can verify on your own.